Okay class, let's continue with dimensionality reduction, second part of the video for subtopic 1.5. What is dimensionality reduction and dimensionality reduction methods? Okay, dimensionality reduction is the process of reducing the number of input variables or features, okay, in a data set. The goal is to simplify the data while retaining its essential characteristics, making it easier to analyze, visualize, and model. The methods are PCA, Principal Component Analysis. It's a very popular method. It's a linear method that transforms the original features into a new set of uncorrelated variables called principal components. And it tries to retain as much variance as possible in fewer dimensions. Okay, next method is attribute subset selection. It selects the subset of the most relevant features. When they say relevant, the meaning of relevant you should know, it's either can be important or significant features from the original data set. It can be done through filtering or wrapper methods. As I teach you last time, I hope you remember or recall back, when it's come to feature selection method, there are three categories: filter based method, wrapper based method, and also embedded method. Okay, filter method basically is very simple and more towards statistical methods. Wrapper methods, there are some methods which is out of statistical methods, and embedded method will be like combination of or a hybrid methods from filter and wrapper. Non-linear dimensionality reduction techniques like TSNE. TSNE is a T-distributed stochastic neighbor embedding or autoencoders. It's useful for capturing complex non-linear relationship in the data. We know that the data is available in the form of structured and unstructured. So most of the unstructured data, there is a possibility that they can be a non-linear data. Okay, why do we use dimensionality reduction? It reduces the computational complexity. It's helped avoid overfitting by eliminating irrelevant or redundant features. Okay, it makes visualization and interpretation of high dimensional data feasible. So in summary, we can say that dimensionality reduction is a powerful tool for simplifying data sets by reducing the number of features while preserving important information. Common methods like PCA, attribute subset selection, nonlinear techniques such as TSNE are suited to different types of data and analysis needs. Okay, next, what is dimensionality reduction? You can see here the key points are occurs of dimensionality reduction, and then the advantages. We'll see one by one. As the number of dimensions, the features increases, data become increasingly sparse. Okay, this sparsity makes it difficult to find meaningful patterns or clusters in the data. So the density and the distance between points become less meaningful, which is critical for tasks like clustering and outliers detection. So the possible combinations of subspaces grow exponentially, making the analysis computationally expensive and inefficient. So this is the curse of dimensionality. Okay, so how to reduce? So the reduction involves reducing the number of random variables under the consideration, and it achieves this by obtaining set of principal variables that capture the essential information from the original data set. And this process simplifies the data while retaining its core characteristic. The original characteristic of the data set won't be changed when you're doing dimensionality reduction. It only reduces the number of irrelevant features, the features which is not really helpful for your analysis. Okay, so that won't make any difference in your final outcome when you do a modeling. Okay, so the advantages of dimensionality reduction, it's avoid the curse of dimensionality, which means by reducing number of features, the reduction mitigates issues related to sparsity and meaningless meaningless distances, eliminates irrelevant features or reduce the noise. It focuses on the most important features, relevant features or significant features. It reduces the time and space requirement. Okay, simplify the computation and storage needs, making data mining more efficient. And lastly, it's allow easy visualization, reduces 2D or 3D, enabling intuitive visual inspection and understanding. So, dimensionality reduction is a crucial technique for managing high dimensional data. Next, the methods for dimensionality reductions. Okay, we have like feature selection and feature extraction. Okay, under dimensionality reduction methodology, we have a feature selections. Okay, it's identify the subset of original variables or features or attributes that are most relevant to the analysis. On the other side, the goal of this particular feature selection is to retain only the most important features while discarding the irrelevant or redundant ones. On the other side of a feature extraction, it transforms the data from high dimensional space into a lower dimensional space. So the goal is to create new meaningful features that capture essential information from the original data set. Okay, some typical dimensionality reduction methods you can see here: PCA, ASS, and nonlinear. So I already explained these before, right? So hope you guys can recall back from my previous slide. Okay. Next, principal component. Let's see a bit deeper into what is principal component analysis. I'm very sure that you learned this in your statistics because it comes from statistical procedure. Okay, PCA is a statistical procedure that uses orthogonal transformation to convert a set of possibly correlated variables into a set of linearly uncorrelated variables called principal components. Okay, the goal is to reduce the dimensionality of the data while retaining as much as of the original variance as possible. How does the PCAs work? Okay, projection onto a smaller space. The original data is projected onto a smaller space, resulting in dimensionality reduction. So the methods, it compute the covariance matrix. Second, find the eigenvectors or eigenvalues of the covariance matrix. These eigenvectors define the directions of maximum variance in the data, and then select the top eigenvectors corresponding to the largest eigenvalues. Okay, these eigenvectors form a new axis, principal components. Okay, it form a new axis in the reduced dimensional space. So it projects the original data onto this principal component. So the 3D diagrams there, you can see there on the slide, shows a ball traveling in a straight line. Okay, it captured by 3 different cameras there, A, B, and C. The data from all the 3 cameras contain redundancy because the ball's movement essentially one-dimensional, a straight line, but the cameras capture it in higher dimensional space. When they say higher dimensional space, it's more than 2 dimensions or 3 dimensions. There is a possibility that more higher number of dimensions. So here the PCA help to identify the underlying one-dimensional trend, the direction of the ball's movement. They project the data onto this lower dimensional space, efficiently reducing redundancy. So the benefit from this PCA is reduced computational complexity, eliminates the noise, irrelevant features, and also makes the visualization interpretation easier by reducing the dimension. Okay, let's see. This one is actually the method okay, this one is for the method part. Given n data vectors in an n-dimensional space, PCA aims to find k less or equal to n orthogonal vectors, principal components, that best represent the data. Okay, the goal is to reduce, obviously it's reduce the dimensionality, but as possible we try to maintain the original variance. Okay, the steps. The first step is to normalize the input data. It ensure each attribute falls within the data same range to avoid the bias towards variable with larger scale. Second is compute the k orthonormal vectors. Okay, find the k orthonormal unit vectors, which are the principal components, and these vectors define new axis, okay, in the reduced dimensional space. Third one, linear combination. Each input data vector can be expressed as a linear combination of k principal component vectors. And then sort the principal components. Okay, the principal components are stored in order to decreasing the significance or the strength based on the amount of variance they explain. And then okay, these are the general steps, okay, for PCA. And remember, PCA works for numerical data only. Okay, however, there are possibility of whatever methods that we use, there will be advantages and disadvantages, and depends on the situation that we apply it. Okay, in certain situation or certain data set, PCA is good. On certain data set, PCA is not good. So on that point, we need to modify the algorithm or the method. Either you can hybrid, you can add on 2 more methods, okay, together, or separately, like, you know, which is dimensionality reduction method 1, method 2, and then go on for the modeling process and so on and so forth. Okay, next is attribute selection. Okay, the attribute subset selection also is reduce the dimensionality data. Okay, the purpose obviously reduce dimensionality. It focuses on identifying and retaining only the most important features or the attributes. Okay, this one is not features, it's supposed to be attributes. Okay, redundant attribute. What is redundant attribute? We know that redundant means it's repeated records or repeated attributes that duplicates much or all the information contained in one or more attribute, more the other attributes. Example, the purchase price of a product and the amount of sales tax paid. Okay, these two attributes are highly correlated and one can be considered redundant. Okay, irrelevant attributes. We know that it contains the information which is not really useful for your data mining task. Okay, example, a student's ID number is often irrelevant when predicting their GPA, as it does not provide any meaningful insights. We know that we need to know, okay, who is the student, but we don't have to know about the student's ID, because other feature is the one going to contribute in order to predict their GPA. Okay. Next, heuristic search in attributes selection. Okay. It's actually a combinatorial explosion with the D attributes. There are 2 power of D possible combinations of attributes are there. Okay, so this exponential growth makes exhaustive search computationally infeasible. Okay, infeasible for even moderately sized data sets. The heuristic attribute selection methods provide efficient strategies to navigate through the vast search space without evaluating all the possible combinations. Typical methods on these heuristic methods are best single attribute under attribute independent assumption, AIA. This uses significant tests like statistical tests to evaluate each attribute independently and select the best one. Second is stepwise feature selection. It starts by selecting single best attribute. and then iteratively adds the next best attribute that improves the model when combined with the previously selected attribute. Okay, next, stepwise. Previously is a best stepwise, now stepwise attribute elimination. It's begin with all the attributes, repeatedly remove the least important, which means not really important, or significant, not significant. Attribute based on some criteria, example, impact on the model performance. Okay, next, best combined attribute selection, elimination. Okay, we learned about best stepwise feature selection. Okay, after that, stepwise attribute elimination, and this one is combination of selection and elimination. It's combined elements of both selection and elimination to balance heading and removing attributes iteratively. Optimal branch and bound is users attributes elimination and backtracking to systematically explore the search space while pruning unpromising branches. It helps find a linear, optimal solution more efficiently than the exhaustive search. And why use heuristic? Heuristic methods significantly reduce the computational complexity compared to exhaustive methods or search. They provide a practical way to handle large data sets where evaluating all the combinations is impractical. Next, attribute creation, or also known as feature generation, is a technique used to enhance the quality and effectiveness of data by creating new attributes that better capture important information. Okay, the objective is to generate feature that can represent the important information in a data set more effectively than the original attributes. Okay, there are three general methodology. First one is attribute extraction. The domain is the techniques tailors to specific domains or application. So it's mapping data to new space, which means it's transforming data into different representation space to uncover the hidden patterns. Whatever it is, the general part of data mining is to uncover or discover the hidden pattern which is hide inside the data set. Okay, for example, for attribute extraction, there is a Fourier transformation, wavelet transformation, and manifold approaches, not covered in details here. Okay, these are some examples of methods. Next, attribute construction. It's combining existing features to create new one, and useful for capturing complex relationship between the variables. Examples are discriminative frequent patterns discussed in advanced classification algorithm. And lastly, for the data discretization, it's converting continuous features into categorical ones. Helps to simplify and can improve model performance, especially for the algorithm that work better with discrete inputs. You know, right? The data types can be discrete, nominal, and so on and so forth. Next, non-linear dimensionality reduction. It's also essential for handling complex data structures that cannot be effectively reduced using linear techniques like PCA. Okay, PCA is a linear model. I'll go on with a non-linear dimensionality reduction. I don't want to explain again the PCA here because it's already explained in previous slide. So I'll continue with non-linear. When the input data is linearly inseparable, the non-linear methods are needed to capture the underlying structure. The process involves step number 1, proximity matrix construction. Okay, we try to construct proximity matrix P that represent the similarity or distance between the data points. And number 2 is this matrix encodes the relationship in the high dimensional space. Second step, we learn a new matrix with K feature where the K is less 2D, the array preserves the proximity information from the original data, and the goal is to reduce dimensionality while maintaining the essential structure of the data. So from the picture here you can see that we have input data X, okay, with the n tuples and d features. To proximity matrix construction, we construct the proximity matrix, which means represent the pairwise similarities or distance between the data points, and last step is the output, which is X hat. When you see hat up here, we say hex hat. It's a reduced dimensional representation with n tuples and k features. Just now we have d features, right? Here you can see d features. Now we have k features. Next, nonlinear dimensionality reduction, which is kernel PCA. Okay, use a kernel function k to construct the kernel matrix. Okay, to construct kernel functions to handle more complex. Again, it's a non-linear methods. It actually extends PCA by using kernel function. So the goal is to construct the kernel matrix P, where element Pij is equal to kxi, xj, representing the similarity between the data points xi and xj. So the objective is to learn the best low dimensional representation, such as estimated proximity matrix P hat closely approximates the kernel matrix P. The kernel matrix construction. So here the kernel matrix P captures the pairwise similarities or the distance in the high dimensional data or the features space induced by the kernel function. These allow the KPCA to handle the nonlinear relationship in the data that linear PCA cannot capture. Number 3, we have eigenvalue decomposition. So the best low dimensional representation can be obtained by using the top k eigenvectors or n eigenvalues of the kernel matrix P. So these eigenvectors correspond to P principal components in the transformed feature space. So the typical kernel functions you can see here: kxi xj equal to 1 plus xi dot xj power of P. Next, the radial basis function, our RBF kernel, we have kxi xj equal to e power of the exponential, where xi minus xj divided by 2 sigma power of 2. The major formula for the kernel PCA versus SNE, you can see that there is a comparison between KPCA and SNE here. KPCA uses kernel function, okay, while SNE computes the probability based on pairwise distances. First is pairwise similarities. Second, SNE is pairwise distances. Okay. Okay, next is SNE. SNE is a stochastic neighborhood embedding SNE. It's construct lower dimensional space while preserving the local relationship between the data points. It is particularly effective for visualizing high dimensional data sets like 2D or 3D. So the proximity matrix construction, SNE construct the proximity matrix P using the following formula. So we have a following formula, which is Pij is equal to Okay, the proximity matrix construction. So as any construct a proximity matrix P using the formula. The formula also is given there. You can see Pij is equal to e power of negative d 2ij. So you can see here this one. Okay, proximity constructions. The d square is equal to modulus x minus x square divided by 2 sigma square. Okay, where the Pij represent the probability, and this formula captures the similarity between the points based on Euclidean distance. Okay, but somehow this SNE and KPCA, there are differences. There are differences between the methods. Okay, next we have a comparison on non-linear data points versus linear data. Okay. Original data set with a red color and the blue points forming a circular pattern, and the two classes are intertwined and cannot be separated by straight line. Okay, you can see here they cannot be separated. Input data, and then PCA, KPCA, and D is the TSNE. Yeah? So with the 4 different methods there. So PCA transformation is result. PCA fails to make the points linearly separable. Okay, where the model projects the data onto orthogonal axis. Since the original data is non-linearly separable, okay, PCA cannot transform it. That's why it's again we receive the same. I hope you guys can check here. Okay. Cannot transform. When it's come to KPCA, it successfully separates the red and blue points. Can you see? There is a separation. Okay, only slight part is smaller, is added here. So it uses the kernel function to map the data into higher dimensional space where it becomes linearly separable after transformation. So the classes can be easily distinguishable. And sorry. The last one, TSNE. It also makes the point linearly separable. Can you see? Originally, it's like, there is this part is like, they like overlap. But when it's come to here, you can see it's separable. Okay, they can be separable, linearly separable. So it's focused on the preserving local, TSNE, yeah? Preserving the local relationship between the data points. It maps the data into lower dimensional space while maintaining the proximity, neighboring points. So the takeaway from these, comparisons, we can see that linear method is suitable for data that is linearly separable, and non-linear methods like KPCA and TSNE is for handling the complex data. Okay, I guess we're going to come to the end for one more slide, which is heat map of proximity matrix, linear and non-linear dimensionality reduction methods. You can see PCA, KPCA, and also the SNE. Okay, I guess you guys can even notice there is a line there. Okay, this is the line and this is the line there. So the two diagonal blocks indicates the proximity within the two clusters respectively. The two off-diagonal blocks indicates the proximity between the data from two clusters as well. So with non-linear method KPCA and TSNE, the proximity between the data tuples from the same cluster is much higher than the proximity between the data tuples from different cluster, which means the linear cluster. So that's all for subtopic 1.5 is over. So we'll cover in the next video will be subtopic 1.6. Thank you.